A simple regression analysis example. We have information about 50 bank customers, their annual income, and leisure travel spending last year. We're going to see if there is a linear relationship between annual income and that kind of spending. I will use Excel regression tool. Under Data tab, Data Analysis tool, and Regression. From Regression dialog, we need to select X and Y range, and check labels if included, and output. First, Y range. Y is the spending. I will select the entire range of spending, and then X range, predictor, annual income. I have selected labels, so I check labels. Confidence level at 95% is okay. Output range, I will put it in this worksheet. Select cell D1. I will also select residual plots and normal probability plots. Click OK. In summary output, we see our score is about 56%. 56% of variations in spending explained by annual income. In ANOVA table, sum of squares due to regression and due to residual are calculated. Mean square due to regression is dividing sum of squares due to regression by degrees of freedom, and also for residual, mean square due to residual is sum of squares due to residual divided by degrees of freedom 48. You can try these numbers. If I divide sum of squares due to residual by degrees of freedom, I will get the same number as mean square residual. We also have the F number and significance F. F ratio is the ratio of mean square regression over mean square residual. We can test that. The same number and a very small p-value for f-test shows that our model is significant. There is a significant relationship between x and y. We also have intercept and annual income coefficients. So the regression equation will be y equals 43.047 plus 0.0248x. Standard errors are calculated for both coefficients. And t-test. Well, t-statistic, which is used to do t-test, is the ratio of coefficient over standard error. We can try this here. If we divide coefficient for intercept over standard error, we will get the t-stat for intercept, also copying the formula, which is dividing coefficient for annual income x over standard error. We get the t-statistic for this number. Now the p-values. The t-tests done here are testing our coefficient calculated against 0. Here in fact we are looking at the significance of the intercept calculated if it's any different than 0. So the null hypothesis of the test is that the intercept is practically zero, and alternative is that the intercept is significantly different than zero. With the p-value of 0.86, we can conclude that the intercept calculated is not significantly different than zero. It's practically zero. But for the slope, the t-test is around the hypothesis that our slope of the line is zero. It's not different than zero practically. And the very small p-value shows that we can reject that null hypothesis. The slope is significantly different than zero. Upper and lower confidence intervals also show us that, for example, if we calculated coefficient for intercept as 43 with 95% confidence, it's between negative 461 and positive 547. Zero is within that interval. And for annual income coefficient, the X coefficient, with 95% confidence, that coefficient calculated as 0.0248 is between 0.018 and 0.031. We also have residuals calculated. These residuals and probability output calculated, these are used for developing these two graphs. Residual plot. We can see the residuals or errors of observations are plotted against zero line. So that's the line of zero error, and these are scattered. The errors are scattered randomly around the zero line. If we see a random pattern, then our model is a good model. If we see a curved pattern, or for example, if the errors are concentrated on one side mostly, or errors on lower numbers are much bigger than the errors on larger numbers, then we have a nonlinear pattern. Also, for normal probability plot, we can see the plot of residuals is close to a straight line. If it's significantly deviated from a straight line, then distribution of errors is not normal. By selecting the data points, we can see which columns are highlighted. Also, by selecting the residuals, we can see the annual income is highlighted and the residuals also. So our conclusion for this regression analysis is that annual income explains about 56% of spending on leisure travel for people. Well, the rest of that should be explained by other factors. Our model is significant, and the slope we calculated is significant. The intercept is not significant, so we cannot comment on numbers around zero. The X values around zero. For example, if the annual income approaches zero, or a very small number, we can't use this model to estimate spendings. And that's the meaning of a non-significant intercept.